Okay, again, we have our basic number system, negative and positive numbers. Negative are below 0, positive are above 0. In addition, we have basic operations, addition, subtraction, multiplication, division, as well as more complicated operations such as powers and roots, which undo powers. So given all of that, we can go ahead and make what we call a coordinate plane. Now say you want two things you want to compare, say popularity and wealth. So you can look at this on a coordinate plane. I can go to what I believe that my wealth is, let's say 5, and calculate what my popularity would be based on that, let's say 10. And if you do this over and over and over again and get lots of data, we get what we call a graph, such as a line. But most graphs aren't linear or a line like this. Rather, they're a bit more curvy, such as this graph. So given that we now know about graphs, let's talk about rates. So rates, we're all used to rates, you run at 5 meters per second, a mile in 6 minutes, but what if we're not looking at rates of something technically moving? What if it's something like popularity and wealth? So let's go back to our graph. So let's look at 2 points, A and B on the graph. How do I find the average rate between those points? Well, if I'm going at the average rate and I start at A, well, I have to move in a straight line to get at B if I'm moving at a single rate. So the average rate is just represented by a single line through both A and B. But now let's get a little calculus-y. Let's move A and B a little bit closer together and closer until they're just a single point. This gives us the instantaneous rate at that point, and expressed by the derivative, or dp by dw equals 5. And this is what calculus is all about. It's taking things that we're pretty familiar with, like average rate, and just shrinking them down to a very, very small scale where we can look at things that we previously could not have figured out before. This applies similarly in area. For example, let's say I have a rectangle. Pretty obvious, we all know that rectangle length times width is the area, 5 times 10 is 50. But what if I want to find the area under something a bit more complicated, like let's say the area under this graph? Well, I don't exactly have a formula for that, or do I? Why can't I just take what I know and just split it into smaller pieces? I know how to find the area of a rectangle, so can I just split the area into rectangles? That I can. If we take the area under the graph and just draw a bunch of tiny little rectangles under it, now I know how to find the area of all those tiny rectangles, and the more I shrink the width of those rectangles, the closer my prediction will be to the actual area. And if we shrink it down to an infinitely small size, we do in fact get the actual area. This is expressed by dw, or very small change in width. By very small, we're talking smaller than like the length of an atom type width. And then of course the length is however high the graph goes. And if we do that for an infinite number of rectangles, then we get the area under the graph, which is given by the fancy symbol, the integral, which we've all seen if you've ever looked at any sort of calculus math page. But we don't just have to stop at one dimension. We can do a 3-dimensional graph and find 2-dimensional area using the exact same method, taking what we know that we know is obvious to us and taking something that we don't know that seems impossible and just breaking it into tiny pieces. We can even find volumes using the exact same method. So what's the takeaway here? Calculus isn't some foreign mathematics that just seems impossible to understand. It's simply what you know applied at the very small scale. And it's responsible for basically everything that you've experienced. The fact that I'm giving the presentation right now, the phone that you used to check your email this morning, they're all because of calculus. And if you've ever taken a big problem and split it into smaller pieces, then you've used calculus yourself. So I advise you, keep using calculus, keep taking big problems and managing them more effectively. Thank you.
Nice job, Ben.